Motors are hiding secret abilities for extremely precise control. Join me while I explore. Motors for 3D printers, drones, and camera gimbals all share essentially the same internals, but in most cases, the motor either spins at high speed or utilizes discrete position control. The notable exception is camera gimbals. Somehow, these produce extremely smooth, precise motion at speeds as low as a complete stop. Today we are going to set up this precise control for a single motor and explore a simple application. But first, we have to explore how these motors work. Motors typically create rotation by turning electromagnets on and off sequentially in order to drag a magnet or ring of magnets around in an endless circle. If the motor is spinning fast enough, the magnet's efforts are as fruitless as a dog chasing its tail. But at low speeds, the magnet can catch its tail and bring the rotation to a stop. This results in jittery motion rather than the buttery smooth control we're looking for. For that, we need a fundamentally different strategy for controlling the motor. Enter field-oriented control. Rather than turning coils on and off in a rotational pattern, this method turns two adjacent coils on and off repeatedly, trapping the magnet in a game of monkey in the middle. By carefully timing the coil pulses, we can coax the magnet around smoothly at very low speeds. Today, we'll use the SimpleFOC library to bring this theory to life. SimpleFOC is an awesome open-source project that makes field-oriented motor control possible with hobby-grade electronics. At the expense of continuity, let's take a look at our hardware. Starting with the Pi-Pico microcontroller to act as the brains of the operation. Next, we have a SimpleFOC Mini motor driver chosen to minimize potential integration issues. And to maximize our capabilities, we have a magnetic encoder. Finally, for our motor, we are using a brushless gimbal motor. The hollow motor shaft runs through to the bottom of the motor, providing an excellent location to mount the encoder magnet. Speaking of which, let's head to CAD to design a motor mount. The goal here is to hold the encoder board under the motor with enough space for our magnet. Secondary goals include leaving enough clearance for screw heads and transferring my measurements properly from my calipers to the computer. While we're here, let's also add a part to hold the magnet. Finally, some mounting flanges might come in handy later. And with that, we can send it to the printer. While that mount is printing, I can start wiring the electronics. Starting simple with the screw terminals and headers on the SimpleFOC Mini driver. It's always good to test early. With the power leads connected, we can see if the board powers up. And we have a light, so everything looks good. Speaking of testing, let's make sure this junk drawer Pi-Pico is still functional. I'll just upload the Blink program as a quick check. Well, that concludes the flashing lights portion of the project. Moving on to the encoder. These sensors come in many flavors. This one happens to communicate over I2C. I2C is a serial communication protocol whose main benefit is the lack of TX and RX lines, which give USB connectors their four-dimensional properties. Data goes to data, clock goes to clock. I might even be able to get it right on the first try. What I didn't get right on the first try was the motor mount. Remember the part about transferring measurements from my calipers to the computer? I managed to enter the diagonal distance of the hole pattern as a side length. At least we can confirm that the measurement is correct. So back to CAD for attempt number 2. With the printer back at work, we have time to copy-paste code from the SimpleFOC website, forget to install the library, and realize that while I successfully connected data to data and clock to clock, I accidentally connected ground to a random output pin. With that all fixed, I have just enough time to wave the magnet in front of the encoder and watch the angle change for a few seconds before the motor mount print is ready. This time, everything fits, but it would be nice to have somewhere to mount these electronics. Back to CAD to throw together a quick baseplate. If we actually want to control the motor, we have to wire the motor driver up to the microcontroller. This uses 3 PWM pins and an enable signal, all of which are configured in software. Moving through the SimpleFOC examples, the next test is open loop position control. This test isolates the motor driver from the encoder in an attempt to avoid integration hell. So far so good. These position commands are in radians, so this move from 0 to 6.25 should be about 1 full rotation. If you were watching close enough to see that that was closer to 1.5 rotations, you're more observant than I was. Anyway, with that baseplate print complete, we can mount the electronics and truck right along into testing closed-loop position control, blissfully unaware of the lurking rotation issue. Right, debugging time. After wasting an embarrassingly long time futzing with PID parameters, I found the issue. This totally unlabeled number in the motor initialization is the number of pole pairs of magnets in the motor. My motor has 7, and the default is 11, suspiciously close to 1.5 times 7. And with that, everything is working. Getting that set up was shockingly easy, so let's move on to using our new capabilities. I'm thinking a volume knob for my computer, with a couple tricks up its sleeve. To make this motor look the part, I'll make a quick knob cover. The best volume knobs have detents to give them that clicky feeling, so our first step will be simulating those detents in software. The basic idea is to continuously update the target position of the motor to the nearest detent. That way, when you move the knob far enough from one detent, the target position will update and the motor will feel like it snaps to the next detent. Adjusting the control gain will change how hard or soft the detents feel. This is set up with 8 detents per rotation and a fairly aggressive control gain in order to capture the behavior on video. Changing to 50 detents per revolution and a slightly weaker gain gives this a great feel, not that you can see it. Next, I'll add some limits so the knob stops at 0 and 100% volume. And I'll add a printout every time the current detent changes. This is already pretty cool. The detents feel nice, and the stops at the limits are nice and springy. Now for the tricky part. If I have a control knob setting the volume, but I also try to change the volume the normal way, the two settings will fight each other. But remember, this knob is a motor. We should be able to send it to a position based on the current system volume. We just need a way to keep the detent logic separate from the go to a new position logic. If we check for changes in the target position from the computer, and reset the check when we arrive at a target, that should do the trick. Now to actually connect this to my computer volume. I think the easiest and possibly least robust strategy is to use Python to interact with the volume setting. After copying an example from the internet and restructuring the code a little bit, we can move on to the serial communication. This is just passing strings back and forth to the microcontroller, so the whole setup is pretty simple. Once again, the tricky part is figuring out whether a volume update came from the knob or from the computer. If we keep track of the values coming from the knob, we can see if the system volume changed to some other value, and then we can assume that was from the computer. And with that, we have a unique volume control knob. I can turn it to set the volume, and when I update the volume manually, the physical knob updates as well. I'm not convinced about this whole YouTube thing yet, so please like and subscribe if you want to see more of my tangents.